Welcome to Computer Networks. This is lecture 7. Let me start with a few logistics for the course for the upcoming weeks. As someone already pointed out, homework 3 is taking a lot of time, but it's being done. That's good. Homework 4 has been out for a little bit, and you will realize that it's related to homework 3. So I hope homework 4 will take significantly less time. And homework 5, just parts of it, it has been posted now. Did anyone get a chance to look at that yet? I can just give you a brief overview of it. I encourage you to look at the actual page for details. I am giving you a list of 1,000 different websites, and your task is to come up with a tally for what those websites use as their web server. So that's the task. It will require you to, first of all, understand HTTP to some extent, because that's how you're going to discover what server they use. And it will also require you to automate this discovery process, because you can't do it manually for 1,000 websites. It's just not feasible. Or you're going to use your whole week doing that. And whenever you automate tasks of this scale, again, this is a tiny, tiny scale if you think about the internet, right? But even if we are trying to accomplish a task of this small scale, and we're trying to automate that to the best of our ability, something is going to break. You're not going to be able to automate everything. And one of the things that you have to learn is identify how much effort should you put in automating things, because for these remaining, let's say, 2 cases, it might be faster to just do whatever you need to do manually, rather than write a program that covers 100% of the cases, especially when you're trying to analyze something, study something. So these are some of the things that you'll have to do. Not a lot of programming. If you think about it for a few minutes, what you need to do will become obvious. What homework 5 will also have is practice problems for the exam. I'll try to post at least 5, 6, 7 questions in addition to what is already there. They will not be programming assignments. They will be practice problems, and I will just grade, or we will grade maybe 2 or 3 of them randomly. But I want you to just try to work through all of those problems, because that's the practice problem. No one signed up for in-class student presentations. I encourage you to do that. The way to do that is by posting a message on the thread that asks for participation. This is important because these are little networking related topics. We don't have room for them as a regular lecture, but it'll be really nice to have discussions about them, because some of them might be controversial topics. Some of them topics might have various opinions, and it'll be nice to have a discussion about that. We're going to have part of the discussion online on the board, and during the meeting we're going to summarize that. And the student who takes the lead for that topic should summarize that discussion during the class. If you haven't had a lot of other opportunities to participate in the class, I encourage you to do that. Some of the topics we're going to talk about, they're not going to be purely technical, and that's the interesting part, right? For example, one of the questions that I asked was, should we retire FTP? And there could be various opinions about that. There are no TA office hours this week. There will be additional hours next week to make up for what we don't have this week. Any questions on logistics about homework deadlines and in-class student presentations? Anything? No? Okay. All right. So we're going to continue our survey of transport protocols and what functionality they provide, but we're going to add to our discussion 2 concrete transport protocols. These are real transport protocols used in the internet, and something called EWMA. This is a way to smooth the data. It turns out this is an important technique used in various places within the networking stack, and we're going to study one use of this particular technique towards the end of this lecture. Just a brief recap of what transport layer is. It's basically a protocol that sits on top of the network layer. And what we mean by that is it uses functionality provided by the network layer. That's what we mean when we say something sits on top of something else. And applications sit on top of transport layer, what that means is transport layer is going to provide some functionality that the applications are going to use. But rather than saying that, sometimes, or most of the time, we might just say, application layer is on top of transport, transport is on top of network. That's the common phrase. There are two broad categories of functionalities that are provided by transport layer. First is multiplexing and demultiplexing. This is important because there might be different applications running in a computer, and when there are packets that are coming into the computer, the network stack has to decide the application that should receive the packet depending on the packet type. And usually we use the word port, which is a number that identifies, that tells the stack which application should receive that particular packet. For example, if we have a web server running on Bayou and a packet comes in with port 80, then that packet should be delivered to the web server, not something else. So that's kind of the idea. Then the other major set of functionality provided by the transport layer is error detection and reliability. Error detection is basically adding some information to the packet so that we can detect if the packet has been corrupted in transit. That's kind of the idea. We looked at 3 different examples of error detection techniques. The highest level idea is if we have some idea for what an uncorrupt packet looks like, then we can determine if it is corrupt or not when we receive it. That's the high level idea. And we use this kind of idea all the time, right? Even in daily use. For example, if we see a car that's all mangled up, we know that, okay, it's a damaged car. It's the same kind of idea here. We have an idea for what a good packet or an uncorrupt packet should look like based on the checksums that we might put or parity. And if something doesn't match, then we know it's a packet that was corrupted. It's a bad packet. So the first thing is we want to be able to detect errors. But detecting error does not make delivery reliable. We actually need to retransmit them as required. Right? Once we know some packet is bad, we need to retransmit it so that the receiver receives a good packet, and that we call that reliable delivery of information. There's another reason why we might want to retransmit, which is if we lose a packet in transit, because these packets are going across the internet multiple hops, and if they get lost in the middle, we have to retransmit them. We talked about something called stop and wait protocol. It's basically you send a packet and wait, and the receiver is going to receive that packet and send an ACK. That's the general mechanism. And if the sender receives the ACK, you send the next packet. If you don't receive the ACK, you know either the data got lost or the ACK got lost. We don't know which one, right? But you have to retransmit. And we looked at this diagram, exploring various cases. I think you are all familiar with these kind of diagrams now. Just to give an example, diagram C shows that the frame was transmitted but the acknowledgement was lost, but the sender has no way of knowing if the receiver received the packet or the frame. So the sender is going to transmit the frame again after the timeout. And finally, when it receives the ACK, it knows for sure that the receiver received the packet. Here are some of the problems with stop and wait protocols. You might end up sending duplicate data. Let's look at scenario C again. The receiver actually received 2 copies of the same data. So that's one of the problems. You might have duplicate ACKs, right? When might you have duplicate ACKs? That's an interesting scenario, and that figures prominently in how TCP congestion control works. Why might you have duplicate ACKs?
It times out getting the first one, so you send a second packet,
Mm-hmm.
you send the packet, and then both of the ACKs come back.
Yeah, that's the scenario D, right? So why did that happen?
the timeout was too short for the...
Yeah, so we made a mistake when we estimated what the right timeout should be. So it was a little bit shorter than it should have been. Can't fill the pipe. What does that mean? What is a pipe here? We're talking about network connection. So why are we not able to fill the pipe here? Because we're waiting for the ACK, and we're just not using that capacity. And it's difficult to set the timeout value. We're going to talk about how we might take some steps towards estimating a good timeout value towards the end of today. As a solution to some of these problems, we talked about sliding window protocol. Rather than waiting until you receive the ACK for any packet you've transmitted, you're allowed to send a few of these packets. What that means is you're allowed to have a few outstanding acknowledgments. Why might we want to do this? It increases the utilization to some extent, doesn't it? And why do we need a window? Why not keep on sending packets? Because the network might not be able to absorb all of the packets, or there might be some limitations on the receiver side, the size of the buffer or the rate at which it can process the incoming packets. All right, so that is what we talked about last time. So this is a pretty abstract description of transport and how one might go about building a protocol that provides reliable message delivery. So we're going to talk about two concrete protocols. The first one is called UDP. You have probably heard of it. It's called User Datagram Protocol. It provides an unreliable and unordered datagram service. Before we even start the discussion about the rest of the points there, why would we ever want this? It sounds like a really bad idea. It's unreliable, it's unordered. Yeah, go ahead.
Sometimes you don't need to get every packet through. Like a good example would be, I remember like back in the 90s or something, there was that program called Dial Pad or whatever, where you could make telephone calls through your phone.
Yeah.
But like you don't need to ensure that every single packet can go through. Like if you drop like one packet out of 1,000, it's fine. Your voice still goes through and it sounds normal to the human ear.
Yeah.
And you don't want to spend extra overhead on handling those things if it's something where speed is important.
Yeah, exactly. So those are the two main reasons why this might still be a useful service. Because just like, for example, let's think about the US Postal Service. If the US Postal Service had to guarantee that each, let's say, first-class mail got to the destination, that would require extraordinary resources. Because there's a little bit of flexibility when you design these systems, right? What would it require if we had to make sure that every single piece of mail gets delivered? We need a TCP. But let's think about the physical example, yeah. What would it require? Let's say we want to redesign the US Postal Service so that it can reliably say, or reliably determine if a piece of mail was delivered to the internet.
Track every package.
Yeah.
Chain of custody.
Yeah, exactly. So you have to maintain some chain of custody. You have to track every packet. You probably have to get an acknowledgement from the intended destination. That's a lot of work. So sometimes we probably don't need that. And that was what you suggested. Sometimes you don't want to pay the overhead. For example, we definitely want to pay that overhead if we're US Postal Service for junk mail that they send, right? It's okay, if it gets dropped a little bit, right? It adds multiplexing functionality, which is also very useful. Checksum helps determine if the packets were tampered with or they got corrupted in transit. The endpoints are identified by ports. What does that mean? First of all, what is an endpoint?
Host?
Yeah, it's the host, it's the applications on the hosts. And they're identified by port. What that means is when we send a UDP packet, we say this UDP packet should go to this IP address and this port. And if I'm a network application that uses UDP, and if I'm soliciting packets, I should say, I am at this IP address and this port, so if you need to send a packet to me, send it to this IP address and this port. So the endpoint is identified by port. IP address is the network layer identifier. Port is what UDP uses to determine which application should either source or sync the packet. And checksum helps in error detection. This is what the header looks like. You have the source port. So we all know what ports are at this point. And we have destination port, length and checksum, and data. Why do we need both? When we're sending this packet, we're just sending it to the destination. So it seems like we only need destination port. Why do we need source port? First of all, does everyone understand this question? Because we're trying to send a packet to an application that's running on port 50. So we just need port 50. We should not need source port.
In case you want to talk back.
Yeah, in case you want to send the message back, you need the source port, right? It's like when you send a piece of mail, it's usually a good idea to put the from as well as to address. Why do we need length? We need to know how long the payload is. What happens if the length gets corrupted and becomes a little bit shorter than the payload? What are the consequences? Let's say you receive a packet, you're the receiver, and the actual payload is, let's say, 50 bytes long, but length says 40. What's the problem? What will crash?
Well, it depends on how you, doesn't it depend? Because like when you receive, you tell it how many bytes to receive or whatever.
Mm-hmm.
But
It's going to be missing part of the data that it's expecting to get. So depending on the file type, if
Yeah.
it's text, it'll just leave it off. If it's an object executable or something, it's going to be missing part of your file and it won't run.
Yeah. So depending on how we have decided to use length in our system, it can have various kinds of consequences. As we suggested, if we're using length to read from the buffers underneath, we might not read everything, right? Or let's say it gets corrupted, because this can get corrupted even within a machine. Once the packet has arrived in the machine, maybe there's some other piece of code that is going to write on that buffer and corrupt that, right? Sometimes you might try to get the buffer, pointer to the buffer, and you might want to cast that to a structure, and that's not going to work. So we can have various types of problems depending on exactly what we're trying to do. So that's the UDP header. We already talked about checksum as an abstract description. Here we go once again. I don't think we need to discuss this again. That's the nice thing about video. You can go look at it again from last time, or even look at better sources in the internet. I think I linked an RFC last time that talked about checksum as well. So there's this phrase that people typically use when they're talking about UDP. It's called pseudo header. So this is a little bit different from what you've encountered before. You've encountered headers, right? So what are headers? What is a header and what is a payload?
The payload is the actual data you want to send, and the header is sort of information about the payload.
Yeah, what's in it, who sent it, how long it is, things like that, right? Okay, so we understand what a header is, and we understand what a payload is. What is a pseudo header? Have you heard of it? Yeah. So there's a very interesting email written by one of the networking researchers from a while ago that talks about this particular phrase, what is a pseudo header, and why it exists. Just to summarize, the pseudo header has two things in addition, two fields in addition to what I showed earlier. Can you tell me what they are? Let's look at what I showed earlier. Okay, just keep that in mind. There's two fields in addition to that.
It's got a bunch of zeros and which protocol it is.
Yeah, and then it's the source address and destination address that was not there. I mean, there are a lot of other bits that are not too important, of course, but those are the two main components that just didn't exist in the header. So it turns out when we compute checksum, UDP checksum, we actually include source address and destination address. We compute checksum over those as well as the rest of the header. But source address and destination header, that's not part of UDP header, right? This is actually part of the IP header. So UDP is not operating purely at the transport layer. Does that make sense? Because it's using information from the IP layer when it computes the checksum, for example. When you have network stack, you're not supposed to use information from, for example, the layer underneath like that. Because the entire packet, header plus payload, at a given layer should be just the payload of the layer underneath. Does that make sense? But here we're using source address and destination address. And that's why it's called a pseudo header. It's not a UDP header, but we're using information from IP header. So it's not a purely transport layer information. Does everyone understand that? And there's an interesting story for why it's done the way it is in that email. I think you will enjoy it, reading that. Especially hearing from someone who was a part of this discussion when these decisions were being made. And turns out there are bad consequences to this particular way of computing checksum in UDP. And that bad consequence is when hopefully all of us convert to IPv6, we might have to redo UDP. Why is that?
Not enough bits.
Not enough bits, and the way we are computing checksum, we have to, for example, right now we're computing checksum over how many bits of source address? 32 bits. So now if that changes, we have to change UDP code. The whole point about layers was you could change things independently. But because we've created kind of hybrid here between the network layer and the transport layer, when we change the network layer, we might also have to change the transport layer. So why don't you read that, and if something doesn't make sense, we can discuss it again. Read that email. That's really interesting. So the next problem we're going to talk about is reliability. So far we talked about how to do multiplexing, how to demultiplex, and how to do limited amount of error detection using checksums, right? So next we're going to talk about reliability. So let's say the problem is dropped packets. What can we do to ensure reliable delivery of packets? Yeah. Let's say duplicate packets is the problem, because this is going to happen, right?
Number the packets.
Yeah, we can have sequence numbers. Can we discuss a little bit about why we might get duplicate packets? We already talked about one of the reasons. Right? What are some other possible reasons? So what is the reason we said could result in duplicate packets?
The acknowledgement is lost.
The acknowledgement lost. Okay. What are other possible reasons? Yeah.
I don't know if this is possible or not, but maybe the same packet gets sent to two different routers and they get routed to the same machine like through different paths.
Yes, that could happen. Yeah. How about a bug? This is the real world. It happens, right? When you design a protocol, and let's say you've designed it in a way, you've specified it in a way that should allow no duplicate packets, but you're still going to get duplicate packets because of bugs. Because someone is not going to do a very faithful implementation of that standard. And you're going to get duplicate packets, and if you design your whole system assuming there are no duplicate packets, then it's going to crash, right? So you should always account for bugs. And there is a saying in network protocols and maybe even in software engineering in general, even if you get garbage in, you shouldn't, for example, garbage in, garbage out, that's not acceptable. And what that means is even if the input is bad, you should still be able to handle that. We talk about that even when you design functions, right? For example, you write a square root function, and what happens if the argument is negative? It's the same in network protocols, but it's even more important network protocols because hopefully we deploy these systems in the internet in the hope that anyone in the world can access our service, and there might be bugs, there might be all kinds of other scenarios that we hadn't thought about, and we need to be able to handle those. Packets out of order. So first of all, why might packets be out of order? Let me just describe what that means. What that means is we've divided a file into, let's say, 100 segments, numbered 1 through 100. The receiver did not necessarily receive these segments in that order. It received 2, 5, 1. It received all the segments, but not in that particular sequence. So why might that happen?
Different paths.
Yeah, for example, if you're taking different paths. Or it could be that your transport does not want to wait to know a particular sequence got to the destination. It's just going to send 10 different packets, and maybe the middle one got lost. Let's say if sequence number 5 got lost, and it hears about that, and it's going to send sequence number 5 after 10. Right? So that could be another reason. What you suggested is usually called packet reordering through maybe multipath effects. So how do we solve this problem?
Sequence numbers?
You could use sequence numbers, yes. But you could also do something. Sequence number alone will not solve that problem. Because the application is still going to receive 1, 2, 3, 4, 6, 7, 8, 9, 10, 5. So sequence number didn't really solve that problem. Then you need to reorder it. And when we're talking about reordering, we're talking about doing reordering at a certain interval. Right? For example, the application could say, or the receiver could say, that I'm going to accept out of order packets, but every 10 packets I'm going to make sure that they're ordered before I move to the next one, or next in a 10, something like that. And there's a word for that. It's called receiver window. Basically, you make sure that you've received all those packets in that window. And here's another problem, keeping the pipe full. How do we solve that problem?
Sending multiple packets.
At a time, there's a technical word for that.
Sliding window.
Sliding window, yeah. And there's a even more general technical word for that. Okay, good. We can think about reliability when we're thinking about one link. Let's say we have 2 machines connected with a wire, and just because they're connected with wire doesn't mean the communication channel is perfectly reliable. So we can think about that. That alone is not such a trivial problem, is it? No, because we need to think about all the issues that we talked about. For example, sometimes we could have missed acts, duplicate acts, duplicate packets. We could encounter all the problems that we talked about earlier, even on a single link. Is everyone convinced of that? Is it true that we'll encounter these problems even when we're talking about a single link? We're not talking about the internet. Let's have one computer, another computer connected with a wire. Which of these problems that we are we guaranteed to not encounter in that particular scenario? Or let's say, that's an easy answer, right? But which one is the least likely problem in that particular scenario? We have 2 computers connected with wire.
Keeping the pipe full.
Keeping the pipe full. So what makes you believe that is the least likely problem?
Well, I mean, because the type of connection you're using, it's a lot to megabits.
Mm-hmm. Mm-hmm.
And I doubt you're going to have a problem.
Okay. So does everyone agree with what I just said?
What did you just say?
Okay. So basically, if I understand your answer, you said that we have this fast link, so it's really easy to send information back and get an acknowledgement back quickly, so the pipe would be full. Is that roughly what you said?
Yes.
Yeah, okay. So again, a lot of these things about opinions and also about looking at the same problem from different perspectives, right? So let me give you a hint. So your answer points in the right direction, but it does not cover all the aspects, and I'll give you a hint. Remember last time we talked about considerations that go into determining what is the right rate, both at the sender and the receiver. So what are some of the considerations at the receiver?
How fast that system can handle input.
Yes. How fast can you process packets? So does that give you a hint as to why this would still be a problem? For example, if we have super fast network but really slow computers, what happens?
There's a lot of unused bandwidth there.
Because the receiver might not be able to generate acknowledgments fast enough. The network itself can deliver packets quickly, let's say. And it has the ability to send a lot of packets as well. Low latency, high bandwidth. But if the receiver cannot generate the ACKs quickly enough, we're not going to be able to keep the pipe full. Is everyone convinced of that? How about packets out of order? Can it happen when you have a single link? Yeah, it can happen, right? Okay, enough of that. These problems become easier or harder when we're talking about multiple links. Obviously harder, a lot harder, because we're talking about multiple links of various kinds. We have multiple hosts, multiple hops. Multiple hops means the path from the source to the destination is going to traverse multiple links. And the phrase that you might sometimes hear is, oh, here's the first hop host. What that means is, okay, that's the directly connected host. And to get to the second hop host, you might have to traverse two different links. Okay? And multiple potential paths. And when we're talking about reliable delivery of information, a lot of times that's done using transport protocol that has a notion of connection. And if we have that, there are some issues about how to establish that, how to tear it down. Especially tearing it down, turns out it's a complex problem. It's actually not that trivial. And we're going to have varying round-trip times. So based on what you already know, why is varying round-trip time even a concern? How do we use round-trip time in a reliable transport based on the abstract description?
To set the timeout.
Yeah, to set the timeout. So what's the problem if the round-trip time changes?
Suddenly your timeout is wrong.
Yeah, exactly. Suddenly your timeout is wrong. And which of the three reasons in the top bullet could lead to varying round-trip time? Third one for sure, but maybe the other two reasons also make it more likely, right? But the third one for sure, there's a clear connection. If you're using different paths, very likely they might have different round-trip time. And if the round-trip times are changing, then you have to make sure your estimate for how long you have to wait to receive an ACK should adjust accordingly. And the reason you have to adjust that is because you don't want to wait too long to send, to retransmit a packet, right? But you don't want to wait, you want to wait just the right amount of time. Here's some other difficulties that we might face when we're talking about a reliable transport protocol. First of all, out-of-order packets. We discussed why, one of the possible reasons why we might have out-of-order packets. But sometimes we might receive very old packets, very old packets. Why might that happen? Let's say a machine had some packets buffered, and something happened to that machine so that the CPU got 100% utilization for whatever purpose. It couldn't transmit that packet, and the network thought this machine was dead and started rerouting packets through some other path. And when this machine is finally free and able to transmit that packet, what happens? You get out of order packets, right? We don't know how capable the receiver is a lot of times. So let's say the receiver only has enough buffer for 2 packets. If we have 4 outstanding packets in the network, that could be a problem. Maybe the receiver will not be able to process the packets fast enough. Because the reliability, if you want to make sure the packets are delivered reliably to the intended application, we have to know how quickly the application can process the packets. Let's say the application is capable of processing 100 packets per second, and if you start sending 200 packets per second, then we're not going to have reliability. And there are many unknowns about how the link between the source and the destination is provisioned in the internet. We might know how fast a connection is from our homes to our ISP because that's in the contract, right? When you purchase an internet service for your home, it says you're going to get this much up, this much down. Of course, they lie all the time, but at least they tell you this much up, this much down. But we have no idea what happens beyond ISP, right? So there are a lot of unknowns. Okay, so TCP, or Transmission Control Protocol. Almost no one calls it Transmission Control Protocol. Everyone knows it's TCP. Okay.
Yeah, I did.
So it's a transfer protocol that provides a reliable, connection-oriented, full duplex byte stream. So let's actually parse each of those phrases. Reliably, we already understand what that means, right? And we also understand what some of the challenges are. Now, what is connection-oriented? What does that mean?
A connection has to be established.
Yeah, but what is a connection in the context of a network? Handshaking, yeah. Yeah, and it's just like what we do, when we go meet someone who might handshake that person, just so that there is connection established, right? There is some context established so that you don't have to remind each other this context every time you say something. That's sort of the point, right? When you go walk up to someone and shake your hands, then you can start your conversation. And when you say bye, you don't need to keep on listening. Oh, is this person going to say something? No. And when you say bye, you sort of know that the connection has been terminated, right? It's the same idea. You need to establish connection that involves certain type of handshaking. We'll discuss that. And when we are done transmitting and receiving packets, we are also going to have a very clear notion that this connection is terminated. We are no longer expecting any packets in this connection. So it's establishing that context. And what is that context in computer systems? It might be establishing buffers, allocating some ports, basically putting some state in the kernel so that you can receive, you're ready to receive and transmit packets in that particular context. What does full duplex mean?
Two-way?
Two-way, okay. Yes. So when we establish a TCP connection, we have the ability to send as well as receive information. That's what it means. What is a half duplex?
When you can send or receive?
Yeah, at a time. You still have the ability to send and receive. But when you're sending, you're not allowed to receive. When you're receiving, you're not allowed to send. Are you familiar with any half duplex type system? Some type of wireless communication.
Two-way radio?
Yeah. How about a simplex system? Okay, let's not get there. All right. And finally, byte stream. What does that mean? It's just a stream of bytes. And that suggests that there is a flexibility in terms of how much data we're allowed to send using TCP. We can use TCP to send small or large number of bytes. And even the amount of information that we need to send does not fit in a single packet or a segment, that's okay, because it allows us to send a stream of bytes, because we can keep track of the position of each byte in the overall message. And the endpoint is identified using IP address and port. This is very similar to UDP. Right? There are two topics that come up when we're talking about TCP. We're not going to cover them. They call it flow control and congestion control. We're not going to cover them today. We're going to talk about them in the next lecture. But very briefly, we need to be able to decide how we should pace the sending of the packets. As we discussed earlier, we can't send packets too fast and too slow. And this is a pretty complex problem. And I actually gave you an example from traffic, highway traffic. Even if you have the ability to meter at each entrance ramp, it's still not so trivial to maintain optimal traffic flow in the highways. Why is that? Because it's a distributed problem, first of all, and second, the feedback is not instantaneous. We encounter the same type of issues. And there is congestion control. All right, so let's take a quick break so that you can stretch for a minute, and we'll continue. If you have any other comments about homework, I'm happy to listen. No comments?
Are you still going to give us that grading script?
Oh, well, I haven't made one yet, but if you cover all those input files, that's it.
Okay.
The grading script will be very simple. Maybe you can write one yourself.
I didn't see how you got the other one to work with the diff,
Yeah.
checking the value and checking it.
Yeah.
All those extra flags, I didn't know what all those extra flags were for.
Yeah.
I'll try to look up the documentation on diff, but I still couldn't make sense of what all those flags were.
We use diff with dash free, and then if they're the same, it just doesn't tell you. It only tells
the
you.
default?
The default is to try and tell you how.
Yeah.
To show you inside the file,
I guess it depends on the file type. Because some of them, they'll just say the file's different.
Yeah.
And other times they'll try to be able to find out.
Yeah, if it is binary, it won't show you.
Never try to have a serious.
So probably the way I did it is probably not the best way. I think what you did is probably the better way. So if you say brief, it's just empty or
Dash brief,
that's just brief.
and then it'll either say they're different or it won't tell you anything.
That's probably the better way. So basically, the grading script will be launch your web server and do a bunch of wgets. And then use wget. And I'll just diff the file. But yeah, I'm happy to provide the grading script.
Just curious, because I know you mentioned it earlier, so I was looking for it.
Yeah.
Like I said, I made my own homework too.
Yeah. Could one of you post instruction on how to resubmit? No one has done that yet. So when you get a chance, you guys probably know better actually how to. Because someone was saying there's a little icon somewhere that you're ready to hunt for, right?
Yeah, you have to tell it I want to take back my submission first, and then you can edit it.
Yeah.
Are they still emailing you? Are they still emailing you about it?
Well, not this one. Not yet.
They're going to.
Yeah, they might.
A quick question.
Yeah.
On the MIME types,
Yeah.
I'm reading mine from a file. I just have a file of all the MIME types and reading to check that against
Based on
the
the extension?
yeah, based on the extension. Is that an okay way to do it? And can I just include that file in with my server? Okay.
All right. Okay, so we're going to learn about TCP, and we're going to spend most of our next lecture on TCP as well. This is an important topic, and a very important protocol for the internet. Who has heard of RFC? What is an RFC?
Request for comments. It's in the book.
Yeah. Yeah, it's actually not the best name, actually, RFC, because they evolved into something that they didn't envision that it evolved to. RFCs have become a way to specify the standards for the internet. The original intention was you write it up and you ask people for comments. So if you go to Google and search for RFC 793, for example, you will find a very nice text document that describes what TCP is. It's rather long, but it's worth looking at it just to get a sense for how the protocols are standardized in the internet. And the idea is you're supposed to be able to implement a protocol just by reading that document. That document has to be complete enough that if two different people implement that protocol, let's say even in two completely different languages, they still have to be interoperate. So that document talks about most of the topics we're going to talk about next. And the protocol gets revised over time, and there will be newer RFCs that went obsolete in an earlier RFC.
I have a question.
Mm-hmm.
Sorry, I might have missed it. What is RFC an acronym for?
It stands for request for comment,
Okay,
but
just making sure that's what it stood for.
But if you go by that expansion, you will not understand what it is.
Right.
It's basically the way to specify internet standards these days. So it really should be IS, Internet Standard. But there are different types within RFC. For example, some RFCs are informational. Some are standards. Informational RFCs might document some of the interesting things about some protocols or some properties of the protocol. That's not necessarily standard, right? Or it might suggest how to get a protocol to work properly, what's the best configuration, things like that. Standard would basically prescribe, what each bit is, what are the header fields, and so on and so forth. We're going to talk about the standards process later in the semester because it's important to understand that. Who specifies this? Who comes up with the standards? It's really important to understand that. TCP was born with IP and later factored out. We sort of see that with UDP, don't we? That the artifact of the way in which it originated. We're using pseudo headers, for example, in UDP. It's an end-to-end protocol. What that means is it does not assume much about how the network processes these packets or segments. Most of the functionality needed to implement this protocol, it resides at the ends, not inside the network, not on the routers, not on the links. If you have the flexibility to put the software on the two ends of the network, you can have TCP, even though the underlying network does not provide any additional functionality. That's what it means when we say end-to-end protocol. And there is an alternative idea. We have been talking about mostly reliability today. That's what we're going to talk about. One way to ensure reliability, someone suggested when we were talking about U.S. Postal Service, you could have custody transfer mechanism on each link. Similarly, even in the internet, rather than the end sending an acknowledgement and the original sender sending a retransmission, if we have a custody transfer mechanism in the network, we could ensure reliability. And there are protocols that do that. For example, in the context of delay-tolerant networking, that's a different type of network than the internet, you actually do custody transfer. For example, if you are operating in a scenario when nodes are moving really fast, the links are intermittent, then we might not be able to ensure there is an uninterrupted link between the source and the destination at a given time, in which case we have to store the messages in between, ensure reliability along these hops. A question for you is to really think about, does the hop by hop or link by link reliability work in the internet, and is that a good idea? Any initial thoughts on that? I want you to think about it on your own, and maybe we can can conclude our discussions in the next lecture. But any thoughts as to whether link by link reliability is a good idea or a bad
Too much
idea?
overhead,
Yeah.
because then all the
Uh-huh.
every link along the way has to be able to keep track of everything that they
Yeah.
did
It's a-
receive and send out.
Yeah. So I totally agree with your point. So, who does not agree? That's the main factor that we should think about when we say does it work or not. Are there? Yeah. Go ahead.
Well, I think that as our technology gets better,
Uh-huh.
this overhead's going to become less and less.
Okay.
So maybe as far as we go for going forward in the future, maybe we should consider doing it that way. I don't know.
Mm-hmm.
Technology is cheaper and cheaper, and everything's faster and faster.
It depends on which technology improves faster, right? For
You
example.
have to be
Mhm.
you have to be certain that everyone in the system is willing to pay that extra for the extra processing power to handle the overhead. Even
Yeah.
if it's not much, there's going to be somebody that doesn't want to pay it.
Right.
And
So
if you've got one link that's not participating.
yeah. So let me offer a slightly different solution in that case. How about whoever has the capability participates in this hub by hub reliability, and if someone does not, you could always skip over that. Right. That'd be a hybrid type solution. Anyways, why don't you think about it, and we'll discuss it next lecture. Okay. This is what the header looks like. Can you tell me what's going on the top row? What are those numbers?
Which bit it is?
Yes. And how wide are these numbers? How wide is source port?
16 bits.
16 bits. Okay. And how many bits total across the entire row? 32. It starts with 0, right? And what's the number at the very top? Because there are 2 rows of numbers.
The 10 place.
Yeah, it just helps you read faster. Yeah. So we have the ports, source port and destination port. Why do we need these ports? Okay, that's how we identify the endpoints, right? For example, web server, destination port 80 if we're sending a request to the web server. Here's something interesting for you guys. And you should be able to do a little experiment yourself and discover it. So when we send a request to the web server, let's say we want to send this TCP packet to the web server. So what's in destination port? Standard web server. 80. What's in the source port?
Whatever the client defined as their source port.
Yeah, and how does a client typically define its source port?
They choose one that's not already used by something else.
Yeah, but do you explicitly define the source port if you're just connecting to someone? Just think about how you did the socket calls. When you connect to someone, first of all, you need to create some kind of address structure. That's for the destination, right? Is that true? Right? How about the client? Did you ever say, okay, here's the destination port and here's my port? No, we probably didn't say that. So I want you to think about that, okay? How about sequence number? Why do we need that?
For reordering and whatnot.
Yeah, we need to know the position, this payload's position in the overall message, right? Overall byte stream. One thing to remember about the sequence number is it corresponds to the bytes, not packet numbers. So let's say in the first segment you send 100 bytes, and let's say the sequence number started at, let's say, 0. And next time you send the packet, what should be the sequence number? And there's acknowledgement number, and there are a bunch of other bits, maybe not so important. But what you should be able to do now is at least parse. If I give you this header field, let's say in the exam, I give you this header field and I give you a bunch of byte stream, you should be able to tell me, okay, what is the sequence number there, or what are these flags? Could you do that? Sounds pretty simple now, doesn't it? So here the description. Again, you can go take a look. We pretty much covered all of it. See the window field? that's going to become very important when you start talking about congestion window and so forth. All right. So here are some flags. These flags are these bits. Basically, one bit of information to indicate what type of packet it is. For example, is it a packet that indicates we're going to start a new connection? That's a different type of packet than a packet that actually carries the data, right? There might be a different type of packet that says we're going to terminate the connection. It's a different type. You're going to set one of these fields, these flags, to 1 to indicate the type of the packet.
Are they mutually exclusive?
They're not. You can have multiple flags set. These are some of the flags. So there's a flag called urgent data. So how does the sender use this data, and how does the receiver interpret it? Any ideas? Any guesses?
Which one?
Urgent.
If there's like a priority queue, then maybe it goes to the top.
And how about the receiver?
Maybe it knows it's something that it was supposed to have already but doesn't have yet.
But it's a little bit vague, right? That's kind of the point. And a lot of times, some of these functionalities are built in the protocols with good intentions, but they're never used. Let's say I'm in the business of selling some software. I want to sell software to the people and tell them that if you use my software, it's going to speed up your internet access. What should I do? So probably set urgent bit 1 all the time, right? In all of my packets, probably. And if everyone does that, then is that bit useful? Probably not. Okay. So earlier we talked about handshaking, which is the process of establishing the connection, which happens in the process of establishing a connection. So this is how it works. A client, when it wants to start a connection with a server, is going to send a packet with the SYN bit set. So I'm not going to say it like that again, but basically what that means is that bit and that header is set. So I'm just going to call it a SYN packet, just to make it easier. So it's going to send a SYN packet with a sequence number to the server. What's the difference between a client and a server? Again, think socket programming.
Server is listening.
Yes. And client calls the connect, right? And what does server call when a packet comes in?
Sorry, what?
What does the server call? Accept,
Oh, yeah.
right? So a client is also called an active participant. It sends a SYN packet. The server responds. I'm just going to call it a SYN-ACK, just to make it easier. And it's going to return its own sequence number that's unrelated to X. But it's also going to ACK sequence number X plus 1. And the client is going to ACK. So let's, first of all, this is called three-way handshake, and three messages exchanged. Do we need these 3 messages? Could we just make do with 2? Why do we need 3? It's easy to say, okay, this is how TCP works, but it's better to really understand, why 3?
Each side has to acknowledge that the other one is synced up in the right starting point.
Yeah, everyone has to, both sides have to know that the other side, what their expected sequence number is. So that's what the sequence number comes from, and it has to be acknowledged in both the direction that the connection is going to be established. Does that make sense? That's why we need 3-way messages. So that's the connect call. That's listen accept. That is when accept returns. Any questions related to the 3-way handshake that happens when you establish a connection? Okay. How do you terminate a connection? when you call close, you guys have done that, right? You send a fin packet. What does fin packet mean? Just one last time. Yeah. And how do you indicate a packet is a fin packet? You set that bit in the header. The receiver is going to send an ACK for that fin. So now the question is, why are there two different fin packets? And remember, they're separated in time. So first of all, why are there two different fin packets? It seems like we need 4 here, not 3. What's going on? And why are they separated in time? And what are the consequences that they're separated in time? Okay, so those are some of the things that we need to understand. So for establishing a connection, only 3. For terminating a connection, 4. Why is that?
Because both sides has to like close the socket together.
Yes. Both sides have to close the socket. All right. So that's why we need 4. And you need to get an acknowledgement for the fact that the other side knows that you close the socket, right? Okay. But what's the consequence for having these two sets of fins be separated in time? What are the consequences? They're separated in time. It's not simultaneous, is it?
Maybe someone's still sending data and the other one is closed.
Yeah. So it is possible for the socket to be active in one direction, even though you've closed it in the other direction. For example, node 1, let's call the node on the left as node 1. Let's close the socket, right? That means it's not going to send any more packets. It just said, I'm going to close the socket. How about node 2? It hasn't closed the socket. It is free to continue sending the packets. And node 1 will continue receiving the packets until it closes the socket. Does that make sense? So that's the consequence of the possibility that they might be separated in time. And a lot of times they are. So here's a diagram. It's called TCP state diagram. Do you all know how to read state diagrams?
We should.
You should, okay.
I don't know how to read a state diagram. I've never taken a class where I had to read a state diagram.
Okay. All right. So this diagram shows the state of TCP at various times of establishing a connection, sending packets, receiving packets, and closing the connection. It covers all the possibilities that can occur when you have packets lost or certain types of packets that are sent, etc., etc. Let's start at the very top, closed. So this is when we don't have any sockets, when you don't have any TCP connection between the two nodes. So what's the first thing that you do if you want to establish a connection? You send a SYN. So that's the phrase after that slash. Do you see the arrow going from closed to SYN sent? So if you once you've sent SYN, you're in a state you've already sent SYN, right? What else needs to happen for the connection to open? So sending a SYN is not enough, is it?
Someone else has to listen for it.
Yeah. Someone else has to listen for it. And then?
Kind of, when they get it, they're going to have to send a response that says, I received your request.
Yeah, that's an ACK probably, right? Basically you need to have SYN. And then? So you send a SYN, what do you receive? SYN ACK. And then what do you send? Okay. So if you follow these arrows, you'll realize that that is one way to get into the established state. So you have a TCP connection established when you get to that established state. But there are different pathways to going there. Can you tell me what's the other way to get there?
Listen, send a synac, and then synac.
Yeah. So when you're listening, what's the first thing that happens? You actually don't send SYN. You receive SYN, right? And in response to that SYN, you send a synac. And what do you receive? you receive an ACK. So that's the other pathway. There are some other arrows there as well. I want you to just, at home, look at it very carefully. Because it explores pretty much all the possibilities. So these are some of the possibilities that describe how a connection might be established. Now let's think about how to tear down a connection, which I said is the complicated part. So let's say we're in an established state. So what's the first thing that you do when you want to close a connection? You send a fin. So you come to fin wait 1 state. Does that make sense? And then what do you do after that? Yeah, there are three possibilities, right? Depending on what you receive. So let's say you receive an ACK. What do you do in that case?
Go to fin wait 2.
And then? And then you receive a fin, and then you send an ACK, and then you're done time wait. Does that make sense? So there are some other pathways as well. I want you to just look at it carefully. And once you look at this carefully, everything will actually make sense. And we just have a few minutes left today, and there are a few more things I want to mention in the last few minutes. And one of them is, why do we need this time wait? Why do we need that time wait? Why not go to closed directly?
What if there's a delay in the packets getting through?
Yes. And it turns out that's a significant wait. What if last ACK is severely delayed? We want to get all those ACKs, and that's why we want to wait a little bit longer, right? Another reason is we don't want to reuse the port immediately. And what's the problem with that? Because once you close the connection, you no longer have that port, right? And when you start another program immediately, that program could use that port, right? And what's the problem there?
Because the data is still in the pipeline.
Yeah, the data is still in the pipeline, and you're going to receive the wrong packets. And it's going to confuse your application. So that's why you want to actually wait for long enough to avoid that to the extent possible. But if you wait too long, what's the problem?
It's wasteful.
It's wasteful. Right? Has this happened to you? For example, you run a program because you have a designated port, and then it crashes or something, and you try to start your server again. It says you can't bind to that port. Does that happen to you? Why is that happening?
Something else is using the port.
Yeah, but you've already terminated that application. And what's the story? Might be time wait or something similar to that. This is part of the system that does not allow you to reuse the port immediately. And that's the motivation. All right. So we've learned how the connection is established and how the connection is terminated. Just look at it carefully so that you understand all the nuances there. That's not enough to ensure reliable delivery, right? We just, set up the context, and we understood how to, tear down the context. We actually need to retransmit the packet when a packet is dropped. The big question here is, how long should you wait to retransmit? That's the big question. And this is an ongoing research, actually, even after so many years. It's not easy to do that. It's a very complicated problem. What are the challenges in estimating RTT? RTT stands for round trip time. Because we want to approximately wait for round trip time. Because we know if we didn't receive an ACK within a round trip time, the time you would have taken a packet to travel from source to destination and back, then we know the packet is lost, right? If you could estimate that accurately, we don't need to do anything. So here are the two main challenges. One is the round trip time changes for various reasons, as we discussed earlier. Another is we want to be able to do this without injecting additional traffic to the network. Sometimes you might hear this phrase, smoothing the RTT or smoothing any kind of samples. When you just do a round trip time estimation, one way to do that is send a packet and see how long it takes for an ACK to come back, right? So that's a round trip time estimate. if you look at a few of these samples, they might vary significantly. For example, at one time you might get a round trip time of 10 milliseconds, at another time 20 milliseconds, at yet another time 15. That's the problem. So we need a way to represent that in a way that helps us predict what the round trip time is going to be in the future. That's what we're talking about. We can, of course, take the average of the whole sequence. Right? Let's say our round trip time samples are 10, 15, 20, 25, whatever. We could just take a average of all the samples and say, okay, we think the round trip time is approximately this. That's one approach. What's the problem with that?
The longer you've been keeping data for, the less new measurements change it.
Yeah, exactly. And it might not be representative of what's happening recently. Right? Let's say you have data from a whole year. That might be completely irrelevant. What was happening, what was round trip time a month ago is probably completely irrelevant now, right? To address some of that problem, we use this technique called exponentially weighted moving average. The idea is you give greater weight to recent samples. We're still going to compute the average, but we're going to give greater weight to recent samples than the past samples. So the weight that we're giving to each sample, it's different depending on how old that sample is. And why is that? Why is that a good idea?
Because the more recent is the more accurate representation of what the transfer is going to be at that time.
Yeah. So so what you said is absolute right, but there are certain assumptions that you have to make for your statement to be correct. And what's that assumption?
That it's going to be continuing to be that way based on it being close to that time.
Yeah. Or more fundamentally, what we're assuming is there's some kind of inertia in the system, right? For example, what has happened in the recent past is going to be the indicative of what's going to happen now or maybe in the near future. There's some kind of inertia in the system. So let's just do this example and then we're done, okay? So here is one way to compute EWMA. New S is basically the latest estimate for what round trip time is. And we use this basically constant called alpha that determines the weight that we give to a particular sample. So we're going to give a weight of how much is it, 0.8 or 0.2 to the new estimate in this particular case? 0.2, right? And how about the historical value? We're giving a weight of how much? 0.8, right? So let's say at time 0, new estimate is 10. Then with an alpha of 0.8, our round trip time estimate is going to be 8 at time 1, right? But at time 1, we also collected a new estimate of 12, and we can compute again what it might be, and it'll be 8.6. and so on and so forth. So I'll leave you with one other thought related to this. You probably already realized that. This estimator is going to work completely differently depending on the alpha that you pick. You could pick an alpha that's very high, close to 1, or you could pick an alpha that's very close to 0. I want you to think about how differently will this estimator work depending on those extreme values of alpha. You'll realize that it works very differently. Okay, and we can have a little discussion about this in the next class. All right, thanks, guys.